Okay. So what I would like to present today is a collection of ideas, which is the work of many people that you see here, both from inside PNNL and also externally. And also this is work that was funded both by externally by DOE and internally by PNNL. And the topic is multi-fidelity scientific machine learning. So scientific machine learning is a huge topic, and I will focus today just on multi-fidelity, leaving out a lot of other things that we have about scientific machine learning with this nice group of people. And apologies if I go fast. I prefer to cover more topics, but I will give also references to papers, and then you can ask me also for more details. So let me start with what do we mean by multi-fidelity. Multi-fidelity is a situation where you have information that can come with different accuracies or fidelities. And what you want to do is you want to combine this information to get something that is more than the sum of its parts. And we have several frameworks to do that. The first one is what you call the serial framework, and I will explain in the next slide exactly what it is. And this is in particular in the context of operator networks. And in addition to having the general framework, we have used it to reinterpret closure for multi-scale systems as a multi-fidelity problem, and also to reinterpret continual learning as a multi-fidelity problem. The second framework that I will talk about is what we call the parallel. So you will see what is the difference between serial and parallel, and or feature adjacent, then this will become evident in a couple of slides. And then the third framework is the following, that multi-fidelity in general talks about pairs of fidelities, but what you can do is you can consider a sequence of different fidelities. Basically, you can stack physics-informed neural networks and operator networks. And finally, I have one slide to say that all the things that I'm talking about are basically aspects of a much broader framework, but I'm not going to tell you right now so that you can stay until the last slide. And if you're wondering why are we interested in these kind of problems, so, well, we work at the national lab, and existing methods can help us only up to a point, because we are dealing with problems that are very complicated. So this is what I'm writing here, that multi-fidelity operator learning hopefully can allow us to simulate physical systems in regimes that we cannot do right now. So this is the main motivation behind all that. So let me start with the serial multi-fidelity framework. And as the word says here, serial, you expect that this is some kind of a sequence. So we assume that there is some kind of low fidelity block. This could be a low fidelity network, it could be a low fidelity theory, or even a numerical solver. And then the output of this low fidelity block is fed into two blocks, a linear correlation and a nonlinear correlation, which compute the correlation between the high fidelity, whatever we call high fidelity, and the low fidelity. So this is why it's called serial, because you have something which is low fidelity, and then you try to morph it into something which is high fidelity by going through these linear and non-linear correlations. And again, this will be approximated by neural networks. And what you have here, finally, in the loss function could include all the types of information that you have. It could be physics of different orders, multi-resolution, and I will show you right now a pretty substantial example, so you can find more details here. So let's go to a problem that's actually pretty difficult, and this is how to predict the velocity of ice sheets. And what we assume here is that we have multi-resolution. So what you see on the top is what we want to do is we want to use an operator network that will train with the following data. It will take as input the basal friction field, which is the friction between the bottom of the ice and the topography underneath, and the height of the ice, and it will output the two components of the velocity, v sub x and v sub y. So assume that you have two cases. Obviously, the top one is at a coarse resolution, the bottom one is at a high resolution, and you would like to be able to combine data like that. So using that framework that I talked about before, we were able to do that, and now the question is it worth it? So let's see a few numbers. If we use just a single fidelity operator network and you put into Phoenix, which is like a finite element code, we can compute, let's say, 10 samples of this expensive simulation, and you train one operator, and then you look at the mean relative error, and it's really bad. It's almost 70%. Okay? And you say, what can I do? Maybe I can use more data, high fidelity data, which means more expensive simulations. So if you go up to 50 high fidelity simulations and you train a single operator network, a single fidelity operator network, you can bring the relative error down to 5%, which is much more acceptable and more or less what anybody can get right now for problems of this kind of complexity. However, what we can do with the multi-fidelity framework is that we can stay with just 10 high-fidelity simulations, but we add 100 low-fidelity simulations, which are very cheap, okay? And by doing that, with the serial multi-fidelity framework, we are able to maintain this low relative error. So these are the kind of problems that we are looking at, where we're trying to combine things that come with different accuracy. So that is just a straightforward application of that multi-fidelity operator framework. But like I said, we can use it to do other things. First, we can do closure for multi-stage systems. If you're not familiar with what is closure, let me just give you a pretty simple schematic here. Suppose that you have this black trajectory, which is the full order model trajectory. This can be some high dimensional dynamical system. And you can do a projection, which is what people call the exact projection of this trajectory, which is on a lower dimensional space, and this would be the blue trajectory. And then you can do very simple models, which goes by reduced order modeling, which would be the red trajectory, and you can see that at the beginning it's fine, but as you move forward in time, eventually it deviates. And the problem of closure is how can you account for the difference between the blue and the red trajectory in a way that is efficient, okay? So let me just give you very simple equation. Suppose, like I said, you have a high dimensional system of, let's say, ordinary differential equation lives in R capital N. And if you do some proper orthogonal decomposition by collecting data from this high dimensional system, then you can identify the proper, the orthogonal, the empirical eigenfunctions. And what you would like to do is to get a representation of the solution by using only capital R of these eigenfunctions, where capital R is much less than N. So that's the problem of reduced order modeling. And of course, there is a very simple way to get what I said before, which is the exact predicted trajectory, which is the following. If you know what is the exact solution, you can always project it down, right? So this is the very simple way. But of course, we don't know that. Otherwise, why try to do this kind of reduction? So what people do usually, which is a very simple thing, is a Galerkin projection. And this makes sense, right? That you can just, wherever you have U, you can replace it by the eigenfunction, the proper orthogonal decomposition, and then you can get a system which is closed in those coefficients for which live at the reduced space. However, this quickly becomes inaccurate, and let's suppose that you discretize it in time, and if you take this integration, basically this approximation, and you run it in time, it will quickly become pretty inaccurate. So what is closure? Closure is that you want to add at every time step, you want to add a correction which will allow you to get from this simple Galerkin projection prediction to the exact predicted trajectory. So, probably you see where this is going, that we will basically interpret this correction as a multi-fidelity problem. So we can have this prediction from the Galerkin projection, which will be the low fidelity prediction, and then we will add to it a correction which will be computed through this multi-fidelity framework. So then the details are, how do we actually do this computation? If you have here the Galerkin POD, at every step, you have a prediction, which is then fed into this deep operator network closure. You get the correction, and then you bring also the prediction, which you had from the Galerkin POD. You add them up, and this is your new prediction. The most important thing in this construction is not what I said, but how do you actually train it? If you try to do the training, which is usually called offline training, it will not work. It will train very, very nicely, and when you try to use it, the results that you will get will be either inaccurate or even worse, unstable. So what we do here is what we call, and other people actually call, in-the-loop training, which is that during the training, you don't train just for one step at a time, but you train for short trajectories. So whenever you get this corrected output, instead of going back to the next step and using again the ground truth, you bring in your prediction, and you do that loop through multiple time steps. In this way, during training, what the deep net closure here learns to do is to correct itself. So this is this in-the-loop training that goes by different names in different domains, but it has proven so far to be a very, very good way to stabilize and also make the predictions accurate. So let's see again a pretty difficult example, which is a problem of two-dimensional Navier-Stokes equations where you have two vortices that merge and you want to predict how do they evolve. So here we have given ourselves kind of a difficult problem because we want to start with a full order model, which is a finite difference method with a pretty small time set, 10 to the minus 4, and we want a reduced order model to use only 10 Galerkin PO modes and a step size which is 100 times larger. So this is a difficult problem, and we want to train the problem without having to solve the full system many times. So we use here 5 Reynolds numbers between 1,000 and 2,000. We use here different orientations for the time zero relative orientation between the two vortices, and we train with data between 0 and 20. So the results I'm going to show you are actually extrapolation. So we don't have time to go through the interpolation results, but most people are interested in how does this thing extrapolate. So here we will try to extrapolate. We will try to go to Reynolds number which is larger, and even though we trained only from data from 0 to 20, we will go all the way to time 40. So we'll try to go double the time. So let's see what we get. What I have plotted here on the bottom is the relative error that we get in the vorticity. The blue trajectory is the exact predicted trajectory that you could get if you only use 10 Galerkin POD modes. And as you see, obviously, as the time progresses, the error grows, right? Now, the orange trajectory is the low fidelity approximation, which is just a Galerkin POD of its own. And the green is the multi-fidelity. So if you look at this, you say, so what were you telling us about? This thing, the multi-fidelity is even worse than the low fidelity. So what was this whole thing about? Well, what I haven't told you is what is this tau here. This tau is how many steps do you use in the loop training. If you use only one, is what people are calling offline training, and is what I was saying, that if you train it with just this one-step training, the multi-fidelity can be even worse than the low fidelity. However, as you start increasing the steps for the loop training, you go to 5 to 10 to 20, you see that the green one, which is the multi-fidelity, comes closer and closer to the true projection, and it also stays within a reasonably accurate prediction even beyond the time that it was used for its training. Of course, look at this, what happens here at 20. If you overdo it, if you use too many steps for in the loop training, numerical accuracy will kill you, because when you use a lot of steps for in the loop training, you have to backpropagate in time and you accumulate error. So What is the ideal value of tau is still an open problem, not just for us, but for all people who try to do this kind of training. Okay, so continual learning, which again, we can interpret it as a multi-fidelity problem. If you haven't heard about what continual learning is before, here I have a very simple definition. The continual learning is the ability to keep training a machine learning tool when new information becomes available, but you don't want to forget what you have learned so far. If you forget, this is what is called catastrophic forgetting. This is a very important problem, and that's why you see all these dots that you see here are different methods that have appeared. So there is a zoo of methods there that basically follow different approaches. Why are we interested in that? Because we can have issues with data privacy. We can have trouble because you have sometimes data sets which are so large that you cannot process them all at once. And in our case, because we're looking at physical systems, we would like to be able to do long-time integration or complex domains for physics-informed neural networks, and we would like to do this incrementally. So, how can we use multi-fidelity to do continual learning? Suppose that you have trained a network with data from domain A, and you have obtained a model A. The idea here basically is the following, that you can use model A to get a prediction in the next domain, B, which is not going to be a very good prediction, but you can consider it as a low-fidelity prediction, which then you can pass through the multi-fidelity network to get the prediction which is better, which is the model B, which will have taken into account also the domain B data, and ideally it will not forget what you have learned in domain A. All right? So why is this a promising idea, even though it can have its trouble? Because what you are trying to do here is you're trying to learn with every new information what else is that you have to learn instead of starting from scratch. Okay? So, and does this work? Well, I can tell you that by playing around with different methods for continual learning, there is no single method that will work for all problems all the time. Okay? What we found here is that if you compare multi-fidelity with single fidelity, yes, multi-fidelity alone does better. If you use replay, which is a very popular continual learning method, well, what we get in if you do single fidelity or multi-fidelity, you don't see much of a difference. And then we thought, okay, this is weird. How come the multi-fidelity doesn't offer anything in addition to replay? So we dug a little more, and we realized that what the result we were getting for replay with a single fidelity model were actually very fragile to the number of neurons that you have in the network. So what you see here is the number of neurons per layer. So the results that I'm showing here were for 100 neurons. If you use 50 or 25, or then you go to very large networks, the single fidelity with replay didn't work. But the multi-fidelity is very robust. So what the multi-fidelity does in conjunction with replay is that it can give you a very robust continual learning algorithm. And we have used this for also more complicated problems that you can find in the paper. So this is what I have here in the box. Okay, parallel multi-fidelity machine learning. So Wenqian Chen, who is a postdoc at PNNL, tried to use the serial framework that I explained before, and he didn't like it. So he said, I don't like this. I will come up with my own way of doing multi-fidelity machine learning. So he came up with this way, which is the parallel version. In the parallel version, what you do is you take the low fidelity input and the high fidelity input, you put them through a common encoder net, and you go into a common feature space. And you do the multi-fidelity there in the common feature space, where you see that the low fidelity features and the high fidelity features are connected by this simple relationship with the trainable vector lambda. So this is the correlation between the low fidelity features and the high fidelity features, but it's done in the feature space. Then you feed things in a common decoder net, and each one of the predictions goes into its own loss function. So this is why it's called parallel. And of course, instead of 2 levels, you can also think of having multiple levels in parallel. So is this a good idea? Well, again, let's look at a difficult problem. And I'll tell you what is difficult about is the regime that we looked at. This is a very popular problem from fluid mechanics. It's the steady lead-driven flow from two-dimensional Navier-Stokes equation. Let's see what we have done here. I've plotted here the relative error, so this is relative error in logarithmic scale, as a function of the Reynolds number. Low fidelity here is just a numerical solver with coarse resolution. And you see that more or less across the Reynolds number, it does a job which is not very good. You get a relative error which is about 10%, okay? Then we have the blue line here, which is a P, a physics-informed neural network. The physics-informed neural network does very well when you are at low Reynolds number, but when you go to high Reynolds number, the error grows fast, okay? So what we did is we used this parallel multi-fidelity framework where the low fidelity was given by the numerical solver, and the high fidelity was given only by physics, by using the P. So we combined them, and we got the black line, which is the multi-fidelity, which almost across the Reynolds number up to Reynolds number 5000, which is the highest that you will find in the literature now, you get a relative error which is about 10 to the minus 3, okay? And so that's why this appears to be a promising idea, and there are more results now, and this approach can be combined with adaptive weighting and adaptive sampling to make it even more efficient. Okay. Are we out of time? Okay.
Yeah, 5 minutes.
Okay, all right. So I told you about this multi-fidelity, the sequential version, right? Where you go and you have one prediction and then that feeds into another prediction. What stacking does is that it says the following. Suppose that you're looking here now only at physics. There is no data, right? We only have access to physics. So we take a physics-informed neural network and we train it once on a domain. And then we consider its prediction as a low-fidelity approximation for itself. So then we can feed it back into a multi-fidelity framework where we will train again with the same physics. So you do it iteratively. And what you have here is what this schematic shows. This is in particular for the wave equation. You have a prediction which comes from a P at, let's say, what we call a stacking level, at the one stacking level, and it fits into a multi-fidelity framework, and you get the next stacking level. And in this way, you can see here, what we're trying to do basically is that we're trying incrementally to learn smaller and smaller scale features as you go through this stacking process. And for this, for example, problem, for the wave equation, by using small networks, because this is what this framework allows you to do, is that it only has to learn what else is new there. We were able to get through a few iterations to get improvement of about a couple of orders of magnitude. And this is again just with physics. There is no data, and we use the simplest physics-informed neural network without any tricks. So this is good because it can improve whatever you want to use. You can use it repeatedly to get an even better result. You can do the same thing with physics-informed operator networks. And we look again here at an example where we're only using only physics. If you try to train for something like a viscous Berger's equation and you go to a small viscosity like 10 to the minus 4, this is right now, if you look at the literature, basically the most difficult case for the Berger's equation using only physics, okay? The best results that you can get if you use a single network, a single fidelity network, are obtained if you use adaptive weighting based on the neural tangent curve. Okay, these results here in this figure are given to you by this black dotted line. Okay, so what we have here, what I call fixed, is that we do this iteration and we keep the viscosity the same at all iterations. And we are able to get what was the state of the art. However, the nice thing about stacking is that as you do the stacking, you don't actually have to use the same physics again and again. So what we did here with what we call the change, we started with a problem that is simpler. So we started with a problem that has a higher viscosity where you can train better. And as we go through the stacking, we were decreasing the viscosity until we got down to the viscosity that we wanted. And in this way, we were able basically to cut the error by half. And again, a lot more to do with these things, but you can think of this as some kind of simulated annealing, but now it's in the space of operators for partial differential equation. You can find more detail here. And finally, the last thing that I wanted to talk about is these stacking networks with domain decomposition. If you're familiar with what are called finite basis spins basically do a domain decomposition where you consider first one level which has a whole domain, then a second level that maybe has two domains, then 4, 8, etc. And you compute the solution at each point in space as an average of the predictions from the different levels. This is a nice approach. However, it is expensive because you have to train all these levels simultaneously. So what we did here is that through this multi-fidelity, we started with the highest level. After we trained for that, then we fed that into a next level to compute for the two, and then feed this into the next one. So in this way, you can train by using smaller networks and without sacrificing the accuracy. And indeed, this is the last result that I have. We used it here for time domain decomposition for the Allen-Kahn equation. We took as the zero level a single pin, which if you try to train it on its own, it gives you a 50% error. And through a couple of levels, we were able with this stacked finite basis spins to bring the error down to less than 1%. Okay, so just 1 minute to tell you what was this broader framework that I was talking about. All the things that I've been telling you about underneath hide the concept of compositionality. So I try to start with something simple and incrementally build it into something that is complex, okay? This idea, I'm not going to go through all this, is an idea that permeates not just deep learning, but also numerical analysis, probability, high energy physics, even in computer science and computability theory. So underneath all these approaches that have been very popular and very successful in these different domains is the same concept of compositionality. So what we are doing here, it does not live in vacuum. It has connections with a lot of other topics, and hopefully there is a lot more to be said here, and hopefully we will be able to explore this two-way street between these approaches and what we are doing to hopefully improve our method. So thank you very much.